In this section, we will discuss arithmetic and geometric sequences. To begin, let's look at the definition of a sequence in general. A sequence is a list of numbers that are related together by some kind of rule or pattern. For example, consider the sequence given here. Try to identify the rule or pattern that describes this sequence and make a guess of what the next two elements in the sequence would be based on the earlier pattern. As we investigate the terms of the sequence, we see it begins at 1, and then the next number is -1, so the negative version of that. The next term in the sequence is 2, so it looks like every other term increases by 1, and then you get the negative version of that number next, so we have -2 next. Then the pattern continues, we would get 3, and then -3, and then 4, and then -4. So if we were to write out the next terms in the sequence, we would get 5 and -5. And this pattern would continue forever, which is the meaning of the 3 dots. It just says the pattern continues as expected out forever. So this is an example of one type sequence where we can describe the rule or pattern linking all the terms of the sequence. Now, one particularly famous sequence is the Fibonacci sequence, which has been well known since the 13th century. An easy way to describe the Fibonacci sequence is to say that the first two terms of the Fibonacci sequence are 1. So it starts with a 1, and then a 1, and then the rule or pattern that links the remaining part of the sequence is that to find the next term in the Fibonacci sequence, you would need to add the two previous terms. So currently we have term 1 and term 2. So if we were to write down term 3 in the blank, we would need to consider the sum of the two previous terms. So we would take 1 plus 1, which would be 2. That means the third term in the Fibonacci sequence is, because the two previous added together to give us 2. Now to find the fourth term in the sequence, you would add the two previous. 1 plus 2 is 3. Now to find the next term in the sequence, we would take the two previous. 2 plus 3 is 5. And here we were asked to write out the first 10 terms of the Fibonacci sequence. So far we've written the first 1, 2, 3, 4, 5 terms together. I'd recommend that you take a moment to now pause this video and write out the remaining terms till we have the first 10 terms of the sequence, and then unpause to check your work. To find each next term, we just add the two previous. 3 plus 5 is 8. 5 plus 8 is 13. To find the next term, 8 plus 13 is 21. To find the next term, 13 plus 21 is, and to find our 10th term in the Fibonacci sequence, we would add the two previous, so 21 plus 34 is 55, and the pattern continues after that. Now this is not required, but if you're interested, an interesting TED Talk about the Fibonacci numbers and different patterns within the Fibonacci numbers can be found at this link. So we just discussed what makes a sequence in general, and then we looked at one of the more famous sequences in the Fibonacci sequence. Now we're going to describe different classes of sequences. The first is arithmetic sequences. When we're talking about an arithmetic sequence, it is a collection of numbers based on a certain rule or pattern, and in this case, the rule or pattern is very specific. Each term after the first term in an arithmetic sequence has a constant difference from the preceding term. So what that means is if we start here on our first term of the sequence at 29, if this is an arithmetic sequence, then each next term differs by a constant amount. So if we think about it, how would you get from 29 to 31? Well, you would add 2. And notice this pattern is preserved. To go from 31 to 33, do you see that we also add 2? And then to go from 33 to 35, we add 2. 35 to 37, we add 2. So for our first sequence, the pattern is that each term is just found by taking 2 plus the previous term. And that's an example of an arithmetic sequence because each term differs by a constant amount. And there's 2 key ideas that make up an arithmetic sequence. First is the first term A1. So here this 1 is a subscript. Notice that it's of a smaller font and to the lower right corner, so we would read this as A sub 1 or the first term. And the common difference, this is how much they differ by. So for our first example, we would write that the first term is 29 and the common difference is 2 because each term is 2 apart. And if you know the first term and the common difference of arithmetic sequence, you can write out the entire sequence from that pattern. Take a moment to look at our second example and identify if it's an arithmetic sequence, which just means is each term in the sequence the previous term plus a constant difference. And if that's the case, then find the first term and the common difference. I recommend you take a moment and pause the video and work on that. Unpause to check your work. So in this example, we would take our -5 and notice if we add 3 to it, we get -2. Let's see if the pattern holds. To get the next term, if you add 3 to -2, you would definitely get 1. The pattern's holding so far. To get to the next term, 4, we also added 3. And then to get to the next term of 7, we also added 3. So the pattern holds in our second example, where we would say this is also an arithmetic sequence. And in this case, the first term would be -5. And we determined that the common difference was 3. Now for our next term, we notice to go from 8 to 3 is actually subtracting 5. To go from 3 to -2 is subtracting 5 again. To go from -2 to -7 is subtracting 5 again. From -7 to -12 is subtracting 5 again. So in this case, we have an arithmetic sequence where now our common difference is a negative value because the values of the sequence keep decreasing. So our first term is 8. And the constant difference in this case is negative because the values of the sequence are decreasing. Now you can always write a formula for an arithmetic sequence. You can find the general nth term, which we would describe as a subscript n, if we know the first term and the common difference by this formula. The nth term of an arithmetic sequence is always equal to the first term plus n minus 1, and here n is our variable, times the common difference d. So in our next example, we're asked to write the first 6 terms of an arithmetic sequence. Remember, when you're told something's an arithmetic sequence, that's giving a lot of information away. That's telling us that each term in the sequence differs by a constant amount. Not only do they tell us it's arithmetic, but they tell us the first term, and they tell us the constant difference. So that means we're going to start at 4, and each term we're going to add 3 to get the next term. So 4 plus 3 would be 7, 7 plus 3 would be 10, 10 plus 3 would be 13, 13 plus 3 would be 16. Now let's count how many we have written down. 1, 2, 3, 4, 5. We were asked to write 6. So 16 plus our common difference of 3 would give us 19. So this is the first 6 terms of the arithmetic sequence described. Now in our next example, we're asked to find the 7th term of the arithmetic sequence, whose first term is 4. We could translate this into the symbols of these problems to write a subscript 1 is 4. Common difference is -7. That means our value of d is -7. And in this case, we have a few options. First, you could write out the first 7 terms of the arithmetic sequence, kind of like what we did here. The 7th one would be your answer. Or you could use the formula to build a general expression for this arithmetic sequence and then just evaluate it when n equals 7. Since we've already listed out and seen that approach, let's try the formula approach. In this case, I know that our first term is 4, so that's going to take on the value here. The common difference is -7. And specifically in this case, I'm looking for the 7th term, so I'm looking for a sub 7. Filling in the formula, we would get the 7th term in the arithmetic sequence is the first term of 4 plus, now in the formula, whatever term you're looking for, that's what you subtract 1 from. So I'm going to take 7 and subtract 1, all multiplied by the common difference of -7. Simplify this term by term, so we'd have 4 plus 6 times -7. That's going to be equal to 4 plus -42, which would equal the value of -38. So we know arithmetic sequences are sequences that each next term differs by a constant value to the previous. Geometric sequences are somewhat similar, except instead of a common difference, we now have a constant multiple. So in a geometric sequence, when you start at the first term, to get the next term, you would just multiply by a fixed constant called the common ratio. And then to get to the next term, you multiply by the same common ratio. Let's look at some examples of geometric sequences. So this is an example of a geometric sequence. Take a moment to identify the first term, and then try to identify the constant multiple. How do you go from one term to the next by multiplying by a fixed value? So this is definitely an example of a geometric sequence. The first term would be 1. We write that as a sub 1 as before. But in this case, the common ratio, the constant multiple, is called r. Common difference is called d. Common ratio is called r. And we would ask ourselves, how do we get from one term to the next? Well, as a multiplier, to go from 1 to 5, you have to multiply by 5. And we see that pattern is upheld because 5 times 5 is 25, the next term. 25 times 5 is 125, which gives us the next term. And then 125 times 5 would be 625. So in this first example, we have the common ratio is 5. Let's talk about the next example. To ask ourselves what the pattern happens here, we start at 10. And then to get to 5, well, you know you could either subtract by 5 or divide by 2, or multiply by 1/2. Both are correct options. Now if I think of first subtracting 5, I would want to ask myself, does that pattern hold? So to get to the next term, if I'm still subtracting 5, I'd expect a 0 here, not a 2.5. But since the pattern doesn't hold, I'm going to tell myself this is not a common difference. So next I'm going to ask myself, is there a common multiple? That would make this geometric. So to go from 10 to 5 is multiplying by 1/2. And then to go to 5 to 2.5 is multiplying by 1/2 again. Multiply 2.5 by 1/2 and you get 1.25. Multiply 1.25 by 1/2 and you get 0.625. So the pattern holds that each term is the constant multiple of the previous, and specifically, we would describe this as a geometric sequence with our first term being 10 and our common ratio equal to 1/2. Now I recommend you inspect our next two geometric sequences similarly, and then pause the video and write a similar description as we did for our last two. Unpause to check your work. Our next example is also a geometric sequence because if you start at 2, to get to 6 you'd multiply by 3, and we notice that pattern holds. 6 times 3 would give us 18. 18 times 3 would give us 54. So our first term starts at 2, and the common ratio is 3 in this case. Now for our final example, it is also an example of a geometric sequence where our first term is 2 And to get to each next term, we multiply by 5. That would make our first term 2, but now our common ratio would be 5. So notice that while the last two examples both start at 2, since they have a different common ratio, the next terms in the sequence are markedly different. There is a formula for each geometric sequence. The nth term of a geometric sequence, which we would write as a subscript n, can be found by taking the first term, a sub 1, the common ratio r, and fitting in this format. The nth term is equal to the first term times the common ratio to the n minus 1 as an exponent. Here's an important thing to note. If you were typing this into your calculator, you would write parentheses r, close parentheses, exponent, parentheses, n minus 1, because the entire n minus 1 term is in the exponent here. Let's look at our next examples. Here we're asked to write the first 6 terms of the geometric sequence. We know when we're told it's a geometric sequence, they're giving us quite a bit of information. That means each term in the sequence is found by taking a constant multiple to the previous. And specifically in this case, we're going to start at 2, and our common ratio is -3. So I'm starting at 2. To get to the next term, I multiply by -3. That would give us -6. To get the next term, I would also multiply by -3. -6 times -3. Remember, negative times negative would be positive. Specifically, we get positive 18, and you can always verify this in your calculator. To get to our next term, we would take 18 times -3, and we would get -54. Now, we were asked to find the 6 terms, first 6, and we've only got the first 4. So we continue this process. -54 times -3 would give us our next term. Negative times negative would be positive, and specifically we would get a positive 162. This is our 5th term. To get our final term that we were asked for, we would take 162 and multiply by -3, and we would get -486. So that's the first 6 terms of this geometric sequence. In our next example, we're asked to write a general formula for the geometric sequence given here. First, we can extract a bit of information. We see the first term is 3. And since they already told us a geometric sequence, we're going to be looking for the constant multiple. 3 times 2 is 6. Let's see if the pattern holds. 6 times 2 is 12, holding so far. 12 times 2 is 24, keeps holding. 24 times 2 would be 48. So we could say the first term is 3, and the common ratio is 2. And we have a formula for the general equation. We would say a to the n is equal to the first term, which is 3, times our 2 all to the n minus 1 as an exponent. Make sure as you write this, this is clearly in the exponent, so smaller font and all in the upper right corner of the digit. And this would be our general formula for the geometric sequence. Now for our next example, we're asked to find the 8th term of a geometric sequence, and they give us some information. The first term is -4, and the common ratio is -2. You've got a few methods here. You could just write out the first 8 terms of the sequence, and the 8th one is your answer. That's one approach. Definitely feel free to do that. Another one is that you could work with the formula, so I'm going to remind us of our general formula. The general formula for a geometric sequence takes the first term and multiplies it by the common ratio to the n minus 1. So I can write a specific case for this example. Our formula is the first term of -4 times the common ratio of -2 all to the n minus 1. Now if I specifically want to find the 8th term, that's a sub 8. So everywhere there was an n, we're now going to replace it with the 8. And we would get the first term times the common ratio all to the exponent 8 minus 1, which could be simplified -4 times -2 to the 7th. As we type this in our calculator, we would get, plugging this into the formula, we would get 512 as our answer for the 8th term in the sequence. Remember, the reason our exponent is now 7 because the formula takes the term that you want to be at and subtracts 1 as the exponent to the common ratio that then gets applied by the first term. Now, in our final example, you've got a mix of sequences here and you're asked to label each as arithmetic or geometric. This would be a great time to pause the video and investigate each of these. Remember to label it as arithmetic. That means you can see each term differs by a constant amount, so you should be able to add or subtract a constant term to each previous one to get the next term. If it's geometric, you should be able to multiply each previous term by a constant multiple. So take a moment and pause the video now and identify whether each of these is arithmetic or geometric, and specifically if it's arithmetic, what's the common difference? If it's geometric, what's the common ratio? So pause the video now and work on that. Unpause to check your work. Now, our first example, as we investigate it, we can just first check, is there a constant difference? So to go from 3 to 8, I'd have to add 5. Let's see if that pattern holds. 8 plus 5 would give us 13. 13 plus 5 would give us 18. So it seems like each term, to find the next term, you would just add 5. That's exactly the definition of an arithmetic sequence. And specifically, our common difference is 5. Now for our next term, if we think similarly, 15 plus 15 is 30. Let's see if that pattern holds. If it does, 30 plus 15 would be 45, but that's not what we see here. We see 60 next. So it's not a common difference. We'll go back to the drawing board. 15 times 2 is 30. Let's see if multiplying 2 pattern holds. 30 times 2 is 60, seems to hold so far. 60 times 2 is 120. And the pattern holds, so that tells us that we are geometric, specifically with our common ratio equal to 2. Continuing, to go from -9 to -5, you'd have to add 4. Let's see if that pattern continues. At -5, if you add 4, you'd expect to be at -1. Seems to be holding so far. -1 plus 4 would give us 3. The pattern holds. This next one is arithmetic, specifically with the common difference of 4. And in our final example, 40, to get to 20, if you were having a common difference, you'd subtract 20. Let's see if this pattern holds. 20 minus 20 would give us 0, which we don't see here, so it's not a common difference. Instead, we go back to the beginning and see if it's a constant multiple. 40 times 1/2 is 20. Let's see if it holds. 20 times 1/2 is 10. Seems good so far. 10 times 1/2 is 5. This means it's geometric, specifically with a common ratio of 0.5. And here we have our accompanying textbook homework. Remember, at the end of the 5.7 section, you would find the textbook homework problems. These are the ones that are assigned. They're all odd, so you can check your work in the back of the book. And if you have questions, don't hesitate to reach out via Canvas message or stop by office hours. Here are some hints for 21 and 23, and for 71 and 77.